Good evening. Am I audible? Have I am audible?
Yes.
Okay, thank you. So let's start our interactive section for our fourth week. So in fourth week videos, mostly uh, 1 minute. So we must join. Okay, in fourth week's videos, we were discussing about mostly about energy equation. The course discussed about energy equation, also uh, chemical species balance equation. Chemical species balance equation, and then the practical applications of this CFD in heat transfer and chemical species and transfer problems, and also one core idea of well postedness. Well post. Okay, these three are the major carry takeaway from our week 4 lectures. So let's start our interactive section with, okay, the first question is, for a two-dimensional incompressible flow of air containing water vapor, what are the boundary conditions needed for the water vapor transport equation? So basically the question is about uh, this is mass transfer mostly, or species transfer. Here the question is about what are the best suitable boundary conditions for the water vapor transport equation. So first option is inlet, in the inlet, mass fraction at the inlet and pressure at the outlet and no slip valves. Then velocity at the inlet, mass fraction at the outlet and no slip at the valves. Uh, or mass fraction at inlet and outlet and no slip at the valves. Or velocity at the inlet, pressure at the outlet and specified mass fluxes on the wall. So please inbox your answers. It would be better if you can reflect. Also, uh, if you are finding it difficult, then you can ask doubts. But please try to attempt the question. Okay, here uh, there is first there is flow of air in our two-dimensional domain, and also water vapor is carried or transported through the airflow. So we have to account, the boundary condition should account for both of these. So simply for uh, if it was flow of air, what would be the ideal boundary conditions for a two-dimensional domain? We want to simulate a airflow in a two-dimensional domain. What will be the ideal boundary conditions? It should be inlet velocity and outlet pressure. So here, if you see that uh, happens only here. So these two conditions are primarily required for the uh, simulation of our airflow. Along with the airflow, there is water vapor transport is also happening. So for that, we need water vapor concentration and mass fluxes. So our answer becomes D, where we need water vapor concentration at the inlet and outlet, but this water vapor is being transported with air, like temperature is transported by air or any other properties being transported. Uh, so we have first we need primarily we need the boundary condition for the transport of air. Then with how this airflow can transport the uh, anything water vapor for say how the air can transport it. So that's next thing. So for first, as for any safety problem, we need inlet velocity and outlet pressure. That is the ideal condition. Okay, next question. What are the key challenges in simulating complex chemical reaction mechanisms in CFD? So, as we have studied, we can simulate chemical reactions with CFD. So, when simulating complex chemical reactions, what will be the key challenges? So, the options are large number of species and reactions. That is, in there will be a lot of reactants, and also there will be a lot of reactions happening, and also stiffness of reaction rates. Then uh, difficulty in difficulty in accurately modeling turbulence, or all of the above. You can inbox the answers. So here, stiffness of reaction rates mainly specifies the uh, difficulty in solving the reaction rate equations, the metrics. So actually, all these will contribute to the complexity of simulating complex chemical reactions in CFD. So when the number of species increases, it will primarily increase the complexity and thereby increases the computational cost. And then when this reaction rates, difficult reaction or complex reaction rates are involved, the equations can become uh, hard to solve, and uh, such a situation needs a better uh, reaction rate integration methods, or those equations should be modeled in such a way that the difficulty should reduce. And also when the turbulence is there along with the turbulence alone, it itself is difficult to model. But there are different turbulence modeling mechanisms. But when it combines with chemical reactions, turbulent mixing effect can uh, uh, increase the complexity exponentially. So the right answer is D, all of the above. Next one, which of the following terms is not included in the general form of species conservation equation in CFD? So we have seen our species conservation equation. So which term is not present there? Option A, convection term; B, diffusion term; C, source term; D, pressure term. So please inbox your answers. So if you remember, the species conservation equation will be is dou by dou t of rho a plus del dot rho a u is equal to del dot ya plus r. So here, um, on the left hand side we have the uh, unsteady term, we have the convection time. On the right hand side we have the diffusion time, and and the last we have the source time. So the only time missing from this equation is the fourth one, pressure time, because for a species transport, pressure is not directly involved. Uh, it pressure in influences the fluid flow, which indirectly affects the species transport. So also in the equation, the question was about which of the following term is not included in the general form. So here, if you see, there is no, as like in our momentum transport equation, we don't have a pressure term in this equation. So our answer is D. The diffusion coefficient in a species. Next question. The diffusion coefficient in the species conservation equation represent what? It represents the rate of chemical reaction. Option B, the resistance to species movement due to concentration gradient. Option C, the bulk movement of species by fluid flow. Option D, the effect of pressure on species concentration. Option E, the total mass of species in the system. So when we are doing uh, simulations, after doing simulation, we need to physically interpret our results. So suppose we are getting some values, or we have to give some values for the simulation, then we should know what is the physical meaning. So this is such a question. What is the diffusion coefficient? So we have the diffusion coefficient in species conservation equation. So what is that particular term in the species conservation equation represent? You can inbox your answers. Actually, the you can decipher it from the question itself. Um, it is known as diffusion coefficient. So if you try to think what is diffusion, literally what you mean by diffusion, then it's easy. So the word meaning of diffusion is kind of dispersion, to disperse or slowly spread, that kind of thing. So if the rate of chemical reaction is kind of rate, it's a time dependent thing, so it won't be there. Then the resistance of species, uh, resistance to species movement due to concentration gradients. So it has to disperse mean it has to infiltrate to the neighboring portions. So that resistance is what is known as diffusion coefficient. So bulk movement is uh, considered by the is handled by the advection type. Effect of pressure, we have already seen that pressure doesn't have much uh, effect on species concentration, and total mass of the species in the system is entirely handled by different equation. So the diffusion coefficient, so the diffusion coefficient, essentially what diffusion coefficient deals with is the resistance of a species, resistance to the species moment against the concentration gradients. Moving to next question. Consider in a CFD simulation of a combustion reactor, which of the following boundary condition is most likely used for the species concentration at inlet? So, in the question, it's asking the inlet boundary condition, and also the question is most likely condition, because most of the options can be taken as inlet boundary condition. The question is for the best suited. So the options are zero gradient, uh, second one, option B, fixed value, option C, mass flow rate, mm, uh, option D, user defined function, also known as UDF, where when it's a function of something, we have to, it's not a direct value or something that we have to, suppose it's a coupled system or something. In such cases, we need something called user defined function. We can give the boundary condition as a function of some other variable or parameter. And the last option, pressure outlet. So outlet pressure, uh, last one cannot be because it is pressure outlet. So among the five options, which is the best suited inlet boundary condition for a species concentration equation? You can inbox your answers. Okay. Mostly in species transfer problem or some other transfer problem, uh, as in our first question, if it was a water vapor transfer problem, then the concentration would have sufficed, but here it's for a combustion. So as like other thing, we need a Dirichlet boundary condition or a fixed value for the inlet concentration. We can't take a gradient for that. We need a fixed value for the Dirichlet boundary condition. That too explicitly defined Dirichlet boundary condition. Next question. In a numerical uh, uh, Redditor's simulation, in a numerical simulation of the species conservation equation, the discretization method commonly used is. Options are first one direct integration, option B finite difference method, option C finite element method, option D finite volume method, option E Monte Carlo method. It's a simple question you can easily answer. Please inbox your answers. Yes, as you know, it is finite volume method. Mostly in CFD, we tried most of the researched or developed method in CFD itself is the finite volume method. And finite volume method is best for species conservation numerical simulation. And this Monte Carlo method is a simulation method, not only for CFD. It is used for when a lot of uncertainties are there. Uh, it is a probabilistic model. Let's say it's a probabilistic model, probabilistic simulation model, Monte Carlo simulations. So the answer is finite volume method. Next question. A CFD simulation predicts a negative concentration for a species. What is the most likely explanation? So we have done a simulation for species transport uh, problem, and after solving, we got in some areas of the domain or something, we got negative concentration for a species. So what may be the its possible cause? Options are numerical error in the discretization, incorrect boundary conditions, C presence of a sink time in the species, D violation of laws of thermodynamics, E insufficient mesh resolution. So which of these can create a negative concentration for a species? Uh, for to simplify the problem, suppose you can uh, think it as a temperature or 2D temperature diffusion problem or something. Uh, the question is, what is the most likely cause of a generation of a negative concentration for a species inside our domain? You can inbox your answers. Yeah, actually, that is a catch. When we see the sync term in the options, we will directly go for that. Actually, the first and the important cause for any negative concentration or negative, in the case of temperature, is negative temperature or temperature inversal, is the discretization fault. We have seen how we are discretizing the equation. Suppose for a whole domain we are discretizing and we are running it in a loop. So a small error in discretization can create a negative concentration or negative uh, value uh, uh, generation inside the domain. So the answer is not the presence of a sync type, but the most probable cause is the discretization fault. Next question. What is the primary advantage of using CFD simulation for studying chemical species, transport, and reactions? Options are high accuracy and detailed results. Option B, ability to conduct experiments in dangerous environments. Option C, cost effective compared to physical experiments. Option D, all of the above. Option E, none of the above. You can inbox your answers. It's not a simple question. Yes, you are right. It is cost effective. Since you don't have to go to this studying chemical species or something, but compared to the other two options, because high accuracy, it's debatable for a CFD. Uh, High accuracy is debatable thing, and detailed results is not possible. So we are limited to the results range, and also ability to conduct experiments in dangerous environments. It's not like that dangerous environment, dangerous, the unpredictability thing we can't uh, model into any CFD simulation. So CFD simulation is uh, essentially a modeling. So that's what's called model. Modeling means approximation. So we are approximating the physical problem. So this is a cost-effective method for simulating or calculating some physical problems. So only answer or only option that left for us is cost option C, which is cost effective cost effective method compared to the physical experiments. And you are right. Next question. In the chemical species conservation equation, what does the convection term represent? Option A, rate of mass accumulation due to chemical reaction within the control volume. Option B, rate of mass transport due to species concentration gradients. Option C, the rate of mass diffusion caused by thermal conductivity. Option D, rate of mass transfer across the boundaries due to pressure differences. You can inbox your answers. So convection. In the last class itself, I think last two classes I have explained what is convection. Convection is actually conduction plus advection. So advection, this term is the bulk movement of fluid. So uh, here it's about mass accumulation. Here it's about mass transfer. This is mass diffusion. Diffusion is, I already told you, it's a uh, slow diffusion to the surroundings or slow dispersion to the surroundings. Then mass transfer, but across boundaries due to pressure difference. So the right answer is mass transfer. Option B, rate of mass transport due to species concentration gradients. Actually, the convection defines how the species is transported. The chemicals, that particular chemical species is transported by the fluid. So, from one in a spatial domain, how it is transported from one any property, it is transported from one place to another by a fluid. It is given by the convection term. So, it is directly in this and the list of our options is matched with the mass transport, rate of mass transfer due to concentration gradients. So, you got the idea. Next question: what factor primarily influences the diffusion coefficient in the species conservation equation for ideal gas mixtures? Options are species viscosity, temperature of the fluid, then molecular weight of the species, then pressure of the fluid. You can inbox your answers. The options are viscosity, temperature, molecular weight, pressure. Okay, the question was for about ideal gas mixtures. For ideal gas mixtures, how the species concentration equation, uh, the diffusion coefficient in the species concentration equation of ideal gas mixture is primarily influenced by which of the following. So, um, for how the viscosity doesn't matter much for ideal gases. And temperature, yes, temperature indeed uh, has influence on ideal gases, but it does not have much influence on diffusion coefficient and molecular weight. Our answer is the molecular weight of the species. I will tell why. The pressure of the fluid, it also has effect, but it pressure mostly have on the convection, advection, the bulk, bulk transport of the fluid. We have seen the previous question. Pressure does not have any direct influence on diffusion coefficient. So our answer is molecular weight of the species. only because it's a ideal gas. Primarily because it's an ideal gas. Because for ideal gases, the diffusion coefficient is inversely proportional to the square root of the species molecular weight. It is called a relation, Stokes-Einstein relation, and which means the lighter species will diffuse more readily. That with Fick's law also, we can know that lighter species diffuses more readily. Next one, when specifying Dirichlet boundary condition for a species in CFD simulation, what information is provided at the boundary phase or at the boundary? Option 1, the species mass flux across the boundary. Option B, species concentration gradient at the boundary. Option C, total mass flow rate at the boundary. Option D, the species concentration value at the boundary. You can inbox your answers. Actually, the same thing we have seen in one of the question before. It's actually some different version of the same question we have attempted before. Can if you can find it, you can inbox your answers. So this word itself gives away the essence of the solution. It's the Dirichlet boundary condition. So uh, giving uh, the Dirichlet boundary condition means giving some value at boundary. So suppose phi is equal to constant at boundary. Such a condition is known as Dirichlet boundary condition. So we are specifically giving some values. So in the list of our options, here it is called flux, here it is concentration gradient, here it is mass flow rate. So only value, the fixed value, the only option talking about a fixed value is the fourth one. So our option is fourth one. Option D, the species concentration value at the boundary. So moving forward, what does the viscous dissipation term in the energy balance equation represent? So we have seen energy balance equation, derivation of energy balance equation. So from that, what does the viscous dissipation term in that particular equation represent? Options are: first one, heat generation due to internal friction within the fluid. Option B, heat transfer due to the radiation exchange with surroundings. Option C, work done on the fluid by external forces. Option D, heat loss due to conduction through boundaries. You can inbox your answers. our energy conservation equation is OCP dot T by dot T plus rho Cp del dot Ut is equal to K del square T plus mu phi V. Suppose I am calling it as 1, 2, 3, 4. Can you inbox which one is the viscous dissipation? Yes, it's the fourth term. Simply we can find it due to the presence of mu itself. So this is the viscous dissipation term, and the viscous dissipation in the fluid momentum equation, we have seen the viscous uh, dissipation equation or viscous terms most gives the effects due to what viscous effects between different layers of the fluid. Here, in looking from an energy angle, the uh, movement between different layers of liquid, different layers of fluid can create energy, heat. So it acts that relative movement between the fluid layers can uh, generate heat. So the option is heat generation due to internal friction of the fluid. So viscous dissipation terms primarily gives the uh, gives the notion of heat generation due to internal friction within the fluid. But in general cases, most of the cases, this viscous dissipation term, this term will be negligibly small compared to other energy transfer due to the heat flux at the boundaries. So in most of the cases, we will be neglecting this term. But that term is needed in the equation to accommodate the energy balance. Going to next question. The energy balance equation in CFD considers which of the following energy transfer mechanisms? The energy balance equation in CFD can simulate or solve which of the following mechanisms? First one, conduction only. Second one, first one, convection only. Second one, conduction only. Third one, convection, conduction and radiation. Fourth one, convection and viscous dissipation only. You can inbox your answers, but the options are poorly framed, I know. Still, you can inbox your answers. Okay, it's not convection, conduction, and viscous dissipation. Viscous dissipation, we already seen that viscous dissipation is we mostly neglect the term viscous dissipation effects. But the answer is convection, conduction, and radiation. So we can simulate uh, uh, all the three convection, conduction, and radiation with the CFD simulations. Uh, when it comes to suppose for a combustion chambers or very high temperature creating environments or something, we have to consider the radiation uh, causing there, radiation heat transfer causing there. So we have to model for the radiation also, and we can model radiation with CFD. So it's called radiation. We are actually taking radiation also uh, uh, radiation transport. We will be taking radiation as another transport property, radiation transport problem. So if I can give some radiation transport, some generic equation, it will be like a balance between emission. We know for radiation there will be uh, three components when radiation is happening. There will be there should be some emission, then absorption, then the third one is scattering or diffusion, that is reflected or scattered. So main three things when we account for radiation transport is emission, absorption, and scattering. The radiation, like we have our left hand side. I'm not writing the actual equation here. So just giving an idea, the radiation emission is balanced by uh, absorption of suppose it is there are two bodies. This is our emission plate, or we have different walls. Suppose the when this is from this our wall, this boundary wall is. I'm not joining this because it can have any shape. So I'm not joining here. So suppose these are four walls, one, two, three, four. So suppose this is the highly, I mean, most heated surface or something, then it can emit radiations, and these can absorb as well as reflect some portion. So the absorption uh, rates minus the scattering rates, plus as we know the other two terms to uh, account for the total direction and position of over the surface. In term of pressure term, we have something like what is it? Intensity or integral term for the overall intensity. Then it will be generation term. So something like this uh, is our generic radiation transfer problem. So like any other transfer property, we can model radiation as a transfer problem. There are different methods used for uh, to model radiation transfer. The most used method is DTM, that is direct transfer method. So moving on to, I'm not going to radiation. Uh, moving on to next question. In the energy balance equation, what does the specific heat capacity represent? Simple question. First in total energy content of a substance per unit mass. Option B, amount of energy required to rise the temperature of a unit mass by 1 degree. Then a rate of heat transfer between two substances. Third one, thermal conductivity of a material. Simple question. Please inbox your answers. That's option B. The amount of energy required to raise the temperature of a unit mass by unit degree is uh, uh, known as specific heat capacity. Next one, how is enthalpy related to internal energy and pressure in the energy balance equation? So the question is about how is enthalpy and internal energy related uh, with internal energy and pressure in the energy balance equation. Option A, H is equal to U plus P, H is equal to U minus P, H is equal to, option C of H is equal to U by P. Option D, H is not related to U or P in the energy balance equation. You can inbox your answers. This is again a simple question. Okay, option A. Do anybody have say that none of the above? Suppose I am giving you an option E, none of the above. If anyone will take it. The answer is option A. H is equal to U plus P. The question is about how it is related. So we don't need the exact equation. So we need the relation. So here in the energy balance equation, we know H is equal to U plus PV in intensive quantities. So the relation is H is equal to U plus P. So just need the relation. Okay. Another one is a numerical problem. Consider a steady state flow of air with mass flow rate 1 kilogram per second and inlet temperature 300 Kelvin. If the heat addition is 2 kilowatt, what is the outlet temperature assuming no heat loss through the boundaries and negligible viscous dissipation? So you have to calculate this, you have to choose your equation, you have to calculate your answer and give me the solution. Options are option A 302 Kelvin, option B 305 Kelvin, option C 308 Kelvin, option D 311 Kelvin. So you can choose the energy balance equation. You can remove the unwanted terms and you can solve and inbox your answers. try to solve the problem. We have here Cp for air, that is 1 kilojoule per kilogram Kelvin. Then mass flow of air, then inlet temperature T in, that is directly given in kelvins, and also heat addition Q is equal to 2 kilowatt. So equate these things, and also how to what will be the sign of this Q? It's the heat addition at the rate of 2 kilowatt. So what will be the sign? Is it a positive sign or negative sign? We know heat and work as we take heat and work as directional quantities. So what will be the sign of this heat transfer? 302. Are you confident it's 302? I haven't checked it actually. So what I have is 305. The equation is simple energy balance equation. MCP delta T is equal to Q, and yes, Q is endothermic, so it's positive. For endothermic, when it's Q enters the system, it is positive. When Q leaves the system, it is, that is exothermic, it is negative. So we have to put m dot Cp T in minus T out is equal to Q. So M we have 1 kg, so 1, Cp also 1, T in is equal to 300, T out we have to find Q. Q is 2 kilowatt. 2 kilowatt is 2 kilojoules per second. What will be the answer? Okay, it's 302. Is it, or 305? Giving answers. I think nobody's giving the answer. Only one person. It's 302. Anyway. So going forward to next question. Which of the following represents a valid Dirichlet boundary condition for the energy balance equation? Options are: option A, specifying the heat flux at a boundary. Second one, specifying a temperature gradient at the boundary. Okay. take it as Newman. Which of the following represent a valid Newman boundary condition for the energy balance equation? Uh, Option A, specifying the heat flux at a boundary, specifying the temperature gradient at a boundary, specifying uh, total heat transfer rate at the boundary, specifying internal energy at the boundary. So, what's the solution? So what we'll do, let's skip this question. Okay, going on to next question. How does the turbulence affect the energy balance equation in CFD simulations? The next question is, how does turbulence affect the energy balance equation in CFD simulations? So, if there is turbulence, first thing, in which term the turbulence effect will be. With that, you try to answer the question. So, options are: it requires additional source term for the turbulent kinetic energy dissipation. Option B, it modifies the thermal conductivity to account for enhanced heat transfer. Option C, it introduces additional radiation terms due to fluctuating temperatures. Option D, it has no significant impact on energy balance principles. So we have four options. First, think if there is turbulence, in which term we have. I have written the energy balance equation before. In which term the turbulence effect will occur. With that, try to answer the question. Can you inbox your answers? Okay, thank you. So the people have responded. It's you're right. Uh, we need an additional source term for the turbulent kinetic energy dissipation. Uh, we know that even the viscous terms are not we are taking since it is less having uh, less effect on the uh, energy transfer. But when there is turbulence, we need the turbulence can create variation in energy dissipation. So for that particular thing, we have to model for turbulent kinetic energy dissipation. So this turbulent kinetic energy dissipation have to be plugged into our energy balance equation through an additional source term. You're right. Going forward to next question. In the energy balance equation, what does the convective term represent? I think we have already asked this, discussed this question today, or it was diffusion. Anyways, the options are rate of heat generation due to internal sources within the control volume. Option B, rate of heat transfer due to temperature gradients within the fluid. Option C, rate of heat transfer due to thermal conductivity across the boundaries. D, rate of work done by the fluid on its surroundings. So we can right away cancel the last option, work done, because it won't be the answer. So try to answer the question. So the question is for convective time. So as we have already discussed, the convective time means due to bulk motion of the fluid. So the fluid is taking away the transporting that particular property. So here the first option is talking about the we have already eliminated the last one because it's one work done. So our first option is heat generation due to internal source. So heat generation this time will be uh, it will be a source term. It won't be the convective term. So next one is heat transfer due to temperature gradient within the fluid. Okay, the uh, heat transfer in within the fluid due to the temperature gradient. That is the fluid is causing the heat transfer due to temperature gradients. So option B is our answer. If you look at option C, it is talking about thermal conductivity. So thermal conductivity mainly uh, uh, has dominance in diffusion. That is conductivity in conduction problems. That is diffusion. So option B is our answer. Moving to next question. What physical property mainly influences thermal conductivity in the energy balance equation? So we have four properties here. First one is fluid viscosity, option B fluid density, option C fluid specific heat, option D thermal diffusivity. So which one of the following properties influence the thermal conductivity? Simple minded question. Can you inbox your answers? So in energy balance equation, the thermal conductivity mostly comes in the term of thermal diffusivity. Option D. So viscosity uh, don't have any direct influence on thermal conductivity. Density, okay, if it is pure conduction, then density have a role. But when it comes to convection, I mean diffusion and convection terms are there, then fluid density don't have that much effect. But all the effects of thermal conductivity is directly correlated with thermal diffusivity. Our answer is thermal diffusivity. Next one, how does the energy balance equation differ for incompressible and compressible flows? So the question is on how the energy balance equation will differ for incompressible and compressible flows. First option is viscous dissipation term is neglected in incompressible flows. Option B, the source term can include additional terms for pressure in compressible flows. Option C, thermal conductivity is modified for compressible flows due to variable density. Option D, the equation remains identical with only property values changing. You can inbox your answers. So here first one is viscous distribution is neglected in compressible flows. Does it? It not. Uh, Viscous dissipation is neglected if you are taking only it is inviscid. So our answer is so the third option is on thermal conductivity, and this is not true. So our option is option B. We have to include uh, uh, terms for additional terms for how the pressure and uh, compressibility is related, or we have to model the compressibility in our source term. Next question. In the energy balance equation, the convection term represents, I think we have already done it. Yes. Okay, next question. The source term in the energy balance equation can represent which of the below? Only heat generation due to internal sources. Second option, only heat transfer due to external sources. Option C, both heat generation and transfer due to various sources. D, none of the above. This again a simple question. Please inbox your answers. Yes. Uh, Anyway, the source term from the source term itself, the induction of heat generation term comes to our mind, but heat transfer from the external sources, that is external heat uh, added can also be included in source term. So the answer is C. Both the heat generation and transfer due to various sources. So heat generation modes mostly, as we have discussed, the viscous dissipation and also due to joule heating, or if it's we are simulating some uh, electronic equipment or something, there this how uh, resistance heating can occur. What such term will be added as source terms or heat generation terms within the domain. Also, the external heat uh, coming through the boundaries. Uh, Radiation is a far example, but still, like radiation and all such as heat. Some if there is some heat coming to the system from any other uh, entities or any other ways other than because we have limitation in giving uh, temperature through the boundaries. Other heat transfer occurring to the boundaries can also be added in the source term. So, next question is on well postness of CFD problem. The question is, which property is not essential for CFD problem to be well posed? So, there are four solutions. I mean, so four options. Option A, existence of a unique solution. Option B, continuous dependence on the solution on initial and boundary condition. Option C, finite solution at all points in the domain. Option D, compatibility of governing equation with the boundary conditions. You can inbox your answer. It is from the definition of well-posedness of a CFD problem. If you can recollect what's the definition for well-posedness of a CFD problem, you can answer the question. For a safety problem to be well posed, we know it should have unique solution. It should be solvable at all times, and there should be continuous dependence. A small change in the insular boundary condition should reflect in the solution, and also to it should be solvable. So the governing equation should be uh, compatible with the boundary condition. So all A, B, D will come. So finite points at all domains. This is something called boundedness. That will we will discuss that in coming weeks, I think. So this thing is needed, but it is not directly related to the well posedness. So we have to think in the point of the uh, from the point of the definition of that particular topic well posedness. Okay, next question. Consider for one-dimensional advection equation dou u by dou t plus c into dou u by dou x is equal to 0 to the problem to be well posed for a subsonic case, that is c is equal to less than 0. The boundary condition at inflow, that is x is equal to 0, should specify which of the following. So our option, first option is only u, then next one is uh, only du by dx, then third one both u and du by dx. Option D, neither u nor dou u by dou x. So, which is the essential boundary condition that we need at x is equal to 0. Can inbox your answers. So, option A. You have answered option A. So, uh, advection equation, advection we know, bulk transport due to fluid motion. The dominating part is fluid motion. So for a advection dominated flow, our essential boundary condition at inlet is U. We only need U, but it should be Dirichlet boundary condition. We need specific value or some constant value of U. We can't take any Newman boundary condition, or this is both U and dou U by dou x is kind of a mixed boundary condition. It's called Robin boundary condition. That is also not feasible. And without any values of U, we can't start. So advection is a uh, fluid flow dominated problem. So we need Dirichlet boundary condition of U. Can you take 2 minute breaks? We have uh, can continue after 2 minutes. Okay, next question. In a CFD simulation of incompressible flow, so Uh, in a CFD simulation of an incompressible flow, which of the following is not a crucial aspect of ensuring well posedness? So again, a question on well posedness, but entirely different set of options. Option A, it should satisfy the continuity equation. Option B, imposing appropriate pressure boundary condition. Option C, using a conservative discretization scheme. Option D, employing time stepping scheme with CFL stability criteria. I think CFL stability criteria, current Friedrich Lewis criteria is yet to be covered in the course. I mean, so try to answer the question. Hope everyone's back. Which of the following is not an essential aspect for well posedness? So our options are satisfying continuity equation. We know for essentially for a flow problem to happen, I mean for any fluid motion to happen, we have to from the modeling point of view, it should satisfy the continuity equation. So well posedness criterion says it should be solvable. So for solving, it should satisfy continuity equation and the boundary condition for a flow problem appropriate pressure boundary conditions are also needed. Then other one is next option is using a conservative discretization scheme. So what is conservative? Actually, there are three vital requirements for any CFD schemes. So first one is it should be conservative. Second one, it should be bounded. I think all this will be discussed in coming lectures. Next one is transportiveness. So a conservative discretization scheme seems that the discretization should be conserved. That simply saying, if we are saying suppose this let's assume this is a two uh, control volumes, discretized control volumes. So the flux passing out of this because the two walls, suppose these two control volumes are joined very tightly together. In that assumption, on the fluid or the flux going out of this exit valve for of this control volume A should reach control volume B without any loss. So that is literally what we say from conservativeness. And the finite volume scheme FVM is, as we know, it's an integrated over the domain, so it is inherently conservative. So conservative discretization scheme is that there should not be any numerical jump or numerical loss, uh, value loss in between the boundaries. Such discretization schemes are known as conservativeness or conservative schemes. So the conservative scheme is uh, very much required uh, for solving or to get any solution. So all the three is uh, directly connected to the solution and existence of a solution and unique solution. So only uh, Odd one is CFL criteria, which will be discussed in coming lectures. The CFL is called current Friedrich Lewis criteria. It is a criteria mostly about the stability. Another requirement for a schemes are stability. The CFL criteria gives the conditions for any schemes for the given schemes to under what conditions the schemes become stable. So CFL criteria is also required condition, but not for well posedness. So well posedness, all the first three options are required. Last one, CFL criteria is directly connected with the stability, not for the solution. Solution can uh, exist with even without stability, but for stability we need CFL criteria to uh, limit the errors. Next question: consider the steady state diffusion equation del square u is equal to 0 for a bounded solution in a square domain with homogeneous Newman boundary conditions. Dou u by dou n is equal to 0 on all sides. The following additional constraint is needed for well posedness. So we have a square domain. Okay, it's not an exact square. Assume it to be square. So here uh, it is given that uh, the boundary condition on all four sides is dou u by dou n. That is its Newman boundary condition at on all four sides. Then if we want to solve the steady state diffusion inside this square domain, which of the following uh, criteria or constraint should be satisfied? Option A, specify a unique reference value for u within the domain. Option B, impose a specific integral constraint on the solution. Option C, neither A nor B. You can inbox your answers. We want to solve this steady state diffusion. So in this, we have suppose we have a completely insulated container or something, and there the fluid velocity, it is how it will be rearranged inside that particular volume or area. To solve that, what will we need? What will be our because it's given that on all boundary condition, uh, on every boundary condition, its Newman boundary conditions are given. So there is no uh, digital boundary conditions. Then what else is needed for to satisfy the well posedness? So is it a unique reference value of u, or to impose any specific integral constraint? That is, suppose uh, let's say integral of u in some dx dy, that particular area is equal to some value or something. So this is what means. So we can impose in some conditions. We need to in radiation and a lot of places we will be imposing integral constraints on the solution. Is that what we need here, or we need a unique reference value, or we can't solve it with both of these? Actually, even with we have a lot of Newman boundary condition. There are approaches to convert into Dirichlet, but here from these options we need a unique reference value of u within the domain. We have some values, some uh, value of u in some point of the cell. We have to uh, we can't assume actually obviously, but we have to obviously give from the problem itself should define some value of u inside the domain. Then only we can solve the equation. I mean, well, posedness is uh, uh, talking about the solvability and existence of unique solution. For that, we need some value, some reference value of u within the domain. But if the value is not fixed, I mean, we have a value, but it is not fixed to any spatial point. Even after that, we can solve it without violating uh, with violating the uniqueness. Uh, we have to get a value of u in some reference point. If the value is some random, we are assigning the u value to any random reference points, then the it still get the solution. Solutions will be right, but what will happen is the orientations or the it can be solved, but the mm, arrangement of velocity u inside that domain will change and it will violate uniqueness. So we need some value u to any particular reference point. Then only we can solve it with unique solution. So for a next question, for a well-posed CFD problem, the discretization scheme should be should ideally be which of the following? Option A, explicit, explicit and computationally efficient, implicit and unconditionally stable, or it should be higher order accurate and conservative. You can inbox your answers. Yes, the answer is all of the above. Here, from simply saying, you can saying here it should be conservative. I already told you it should be conservative to solve. Uh, implicit, it, implicit and explicit. Uh, we know we will be giving implicit and explicit uh, discretization to time varying as well as spatial discretizations. So all these schemes can be with all these schemes we can get well posed CFD problem. So all of the above, I mean all the three options, with all the three options, we can attain a well posed CFD problem. Next one, next question. You are discretizing the Navier-Stokes equations using finite elements. So we are here it's finite element method. Which of the following factors can affect the well posedness of your solution? So here we are not discussing in a finite volume method. Here it's for finite element method. For a finite element method to be well posed, which of the following factors will affect? Is it A, choice of the element type? Option B, mesh quality. Option C, order of accuracy of the discretization scheme. Or option D, all of the above. Can inbox your answers. No, it's not just mesh quality. Uh, uh, Actually, all the above, because we are just discussed about the schemes type. So scheme definitely affect. So well posedness is what discussing only about the uniqueness and existence of solution, and it should be uh, instantly uh, it should respond uh, instantly to the any change in the initial and boundary conditions. So all these three, suppose the instant response, if I may, suppose we have a tank uh, and it's connected to a tap or something. So when when the tap is locked, there won't be any water flow. But at the instant when this tap is open, water start to flow out of this tap, and that information is transported instantly to the tank. So this is the instantaneous transportiveness in actually in a physical sense in the fluid happening within the fluids. So this we should capture. So for capturing that, obviously the mesh. So not only the mesh quality, uh, element types also plays a role in creating mesh quality. And again, mesh quality is needed, and also order of accuracy of the discrete schemes. In some cases, due to the complexity of the problem, we may have to go to higher order schemes or higher order derivatives. So in here, in finite, and also we have discussed in previous uh, sessions, in finite element, the solution method itself is different. We are LU decomposition method and all such methods are we are using in finite element methods. So there, all these will be having significant effect on the solution and uniqueness of the solution. So the option D, the last option is the answer. Option D. Next question. Consider CFD simulation of a turbulent flow. How can the presence of turbulence affect the well posedness of the solution? Here it is asking how the turbulence, we have seen different terms, different influence of different times on well posedness. Here the question is about how the turbulence is going to affect the well posedness of the numerical simulation. Option A, it has no impact on well posedness if the turbulence model is properly chosen. Option B, turbulence can introduce additional unknowns, uncertainties, potentially affecting the uniqueness. Option C, it can lead to numerical instabilities if the discretization scheme is not well suited for the turbulence. Option D, all of the above. Please inbox your answers. This will be our last question. The answer is D, all of the above. So here it has no impact on well posedness if the turbulence model is well properly chosen. Uh, so we have discussed before the turbulence has to be modeled properly. We have to there are larger dissimulation, LES is there, RANS is there. All such turbulence modeling schemes are there. If we are choosing the proper turbulence model, then there will be a unique. Then the system will be solvable, and we will get a unique solution. And also, it is true that turbulence can introduce uncertainties and it can create complexities. Also, it can create numerical instabilities if the discretization scheme is not suited for the turbulence. So, option D is our answer. So, that ends our session for today. Thank you. Any doubts?